This week we are going to be looking at the Vespar theory and using that to try to predict the shape that the geometric shape that molecules are going to be formed based on their bonds and their placement of the lone pairs that they have. So an electron domain refers to the arrangement of electrons, including bonds and lone pairs around the central atom, whereas the molecular geometry explains the arrangement of the bonded atoms. With this being said, and there are no lone pairs around any of the central atoms, the molecular geometry will be the same as the electron domain geometry. So for today's presentation, I'm going to be demonstrating these types of molecules using hypothetical terms AB in order to describe the electron domain geometrics. So in a molecule, AB2 can either have 3, 4, or 5 electron domains. So AB2 with 3 electron domains will have a trigonal planar shape, which is an example would be sulfur dioxide. It has one lone pair. The molecular geometry of it would be bent, and like I said, the example would be sulfur dioxide. So it's kind of hard to demonstrate with the balloons, but I'm going to try my best. I have here the pink balloon representing the central atom, and then the red ones for now are going to represent the other geometries, but we'll do the best that we can. Okay, so this having 3 electron domains would look, if it was to be like a bent, it'd be similar to this situation. And then AB2 with 4 electron domains would take a tetrahedral shape. An example of this would be ammonia, and its molecular geometry would be trigonal pyramidal. And so that would look something like this because it has the 3 domains. And then another example of this could be water, so the ammonia that I mentioned has 1 lone pair, but water actually has 2 lone pairs, and it's a tetrahedral shape similar to this for the electron domain, but its molecular geometry would be bent. An example of one with, if AB2 had 5 electron domains, it would have a trigonal bipyramidal shape, an example being iodine fluoride, which has 3 left pairs, and 3 lone pairs, I'm sorry, and it would actually take a linear shape. So even though the electron domain geometry is a little different, and my colors don't apply here, but you would have a linear shape for the actual thing. So I guess it would be more like this. Let's see. So I'm also referencing our textbook, which has the table in it. So the next example that I'll do is another 5 electron domain example. This one's for AB3, and it would be like chlorine trifluoride. It would have 2 lone pairs, and it would be a trigonal bipyramidal shape as well. But because of the placement of the lone pairs, it comes out more T-shaped. So it would kind of look like this. AB4 with 5 electron domains, for example, sulfur tetrafluoride, will also have a trigonal bipyramidal shape and 1 lone pair. And then that's a seesaw shape. So I'm not sure balloon concept so much. If you're supposed to be more focusing on the electron domain geometry, more so than the molecular, but I'm going to stick with the electron domain geometry. So like I said, it's the trigonal bipyramidal. And then one more example that I'll give is the octahedral electron domain geometry, which could come from a total of 6 electron domains. You can have AB4 or AB5, and they would both come with this octahedral shape. And examples of this would be xenon tetrafluoride and bromine pentafluoride, which xenon tetrafluoride would have 2 lone pairs, and the bromine pentafluoride will have 1 pair. So these balloons I'm trying to represent the electron domain geometry. So just to recap, there's the trigonal planar, there's the tetrahedral, like this. There is the trigonal bipyramidal, which is with 5 balloons. I picture it being something like this. And then the octahedral, which is kind of hard to demonstrate, but if I kind of picture it like that. So the takeaway from this is like we're trying to use the valence shell electron pair repulsion theory, which you get from using the correct Lewis structure first, and then knowing that the electrons in the valence shell are the ones that are doing all the chemical bonding, so that's what they use to know whether or not atoms are going to repel one another. And so the model helps predict the shapes because it knows when the electrons will repel one another. But I think it's really important to remember that you cannot tell the shape of a molecule or ion simply from the formula alone. So you need to, know that predicts the arrangement. And it only considers the electron pair repulsions, and there's always a chance for nuclear repulsions or nuclear electron attractions, and that will also affect the final arrangement. For the most part, this is how we can kind of predict the shape of these molecules. And that's week 7 for me. This one was definitely tricky as far as like understanding how to formulate with the balloons. But it's a nice physical, metaphor to look at things and kind of get a better understanding of exactly what is going on with these shapes when we're describing them. Okay, see you next week.